Hi everyone, I'm Roy. Today we will study formulas on the formula sheet. In the last video, I categorized all formulas into 5 groups. Group 1, Basic Electrical Formulas. This group includes some of the most fundamental electrical formulas that you'll need to know. Okay, let's go through the formulas in Group 1 first. I will explain the meanings and the units of each formula. Let's get started. First, let's look at the formula itself. The formula for AC Ohm's law in AC circuits is V equals I ZA. This formula calculates the voltage as the product of current and impedance in an AC circuit. Now, let's break down each variable in this formula. V, voltage. The potential difference that drives current through the circuit. The unit for voltage is volts. I, current. The flow of electric charge in the circuit. The unit for current is amperes. ZA, impedance. The total opposition to the flow of current in the circuit, including both resistance and reactance. The unit for impedance is ohms. This formula helps us understand the relationship between voltage, current, and impedance in an AC circuit, which is essential for analyzing and designing AC electrical systems. First, let's look at the formula itself. The formula for power dissipated in a resistor is P equals I squared R. This formula calculates the power converted into heat in a resistor. Now let's break down each variable in this formula. I, current. The flow of electric charge through the resistor. The unit for current is amperes. R, resistance. The opposition to the flow of current within the resistor. The unit for resistance is ohms. P, power. The power converted into heat in the resistor. The unit for power is watts. This formula helps us understand how much electrical power is being converted into heat in a resistor, which is important for assessing energy loss in electrical circuits. First, let's look at the formulas themselves. The formula for tangent is tan pH equals opposite over adjacent. The formula for sin is sin pH equals opposite over hypotenuse. The formula for cosine is cos pH equals adjacent over hypotenuse. Now let's look at how we apply these trigonometric formulas in electrical theory, focusing on 2 important right triangles, the power triangle and the impedance triangle. Power triangle. In electrical theory, the power triangle helps us understand the relationships between real power, P, reactive power, Q, and apparent power, S, in an AC circuit. Sin of phi equals Q over S, cosine of phi equals P over S, and tangent of phi equals Q over P. The formula for apparent power is apparent power S equals the square root of the sum of P squared and Q squared, which combines real and reactive power to give the total power in the circuit. Impedance triangle. The impedance triangle helps us understand the relationships between resistance R, reactance X, and impedance Z in an AC circuit. Sin of phi equals X over Z, cosine of phi equals R over Z, and tangent of phi equals X over R. The formula for impedance is impedance Z equals the square root of the sum of R squared and X squared, which combines resistance and reactance to give the total opposition to current flow in the circuit. First, let's look at the formula itself. The formula for insulation resistance is R2 equals L1R1 divided by L2. This formula calculates the insulation resistance of a material, given the known resistance at a certain length. Now let's break down each variable in this formula. L1, length 1, the length of the cable 1. The unit for length is meters or any consistent unit of length. R1, resistance 1. The cable 1's insulation resistance. The unit for resistance is megaohms. L2, length 2, the length of cable 2. The unit for length is meters or any consistent unit of length. R2, resistance 2. The insulation resistance of cable 2. The unit for resistance is megaohms. This formula helps us understand that the longer the cable, the lower the insulation resistance compared to a shorter cable. This is crucial in evaluating the insulation properties of electrical materials. First, let's look at the formula itself. The formula for electrical resistance is R equals ROL divided by A. This formula calculates the electrical resistance of a uniform material. Now let's break down each variable in this formula. RO, resistivity, the intrinsic property of the material that quantifies how strongly it resists electric current. The unit for resistivity is ohm meters. L, length, The length of the material through which the current flows. The unit for length is meters. A cross-sectional area. The area of the cross-section of the material perpendicular to the current flow. The unit for the cross-sectional area is square meters. R, resistance. The opposition that the material offers to the flow of electric current. The unit for resistance is ohms. This formula helps us understand how the resistance of a material is affected by its resistivity, length, and cross-sectional area. Specifically, resistance increases with the length of the material and its resistivity, while it decreases with a larger cross-sectional area. First, let's look at the formula itself. The formula for electric charge is Q equals sine CV. This formula calculates the electric charge stored in a capacitor. Now let's break down each variable in this formula. C, capacitance, the ability of a capacitor to store an electric charge. The unit for capacitance is farads. V, voltage, the potential difference across the capacitor. The unit for voltage is volts. Q, charge, the electric charge stored in the capacitor. The unit for charge is coulombs. This formula helps us understand how much electric charge a capacitor can store, which is crucial in designing and analyzing circuits involving capacitors. First, let's look at the formula itself. The formula for capacitance in parallel is CT equals sine C1 plus C2. This formula calculates the total capacitance when capacitors are connected in parallel. Now, let's break down each variable in this formula. C, total capacitance. This is the sum of the individual capacitances in the parallel circuit. The unit for total capacitance is farads. C1 and C2, capacitance of capacitor 1 and capacitor 2. These are the capacitances of the capacitors in the parallel connection. The unit is farads. When capacitors are connected in parallel, their total capacitance CT is the sum of the individual capacitances C1 and C2. This means that the overall storage capacity of the circuit increases, making the parallel connection beneficial for applications requiring higher capacitance. First, let's look at the formula itself. The formula for capacitance in series is 1 divided by CT equals 1 divided by C1 plus 1 divided by C2. This formula calculates the total capacitance when capacitors are connected in series. Now, let's break down each variable in this formula. CT, total capacitance. This is the equivalent capacitance of the capacitors connected in series. The unit for total capacitance is farads. C1 and C2, capacitance of capacitor 1 and capacitor 2. These are the capacitances of the individual capacitors in the series connection. The unit is farads. When capacitors are connected in series, the total capacitance is less than the smallest individual capacitance in the series. Series connections are useful in applications where a lower overall capacitance is needed. First, let's look at the formula itself. The formula for real power in an AC circuit is P equals VY cos theta. This formula calculates the real power doing work in an AC circuit. Now, let's break down each variable in this formula. V, voltage, the potential difference that drives current through the circuit. The unit for voltage is volts. I, current, the flow of electric charge in the circuit. The unit for current is amperes. P, power, the actual power doing useful work in the circuit. The unit for power is watts. The cos theta represents the power factor, indicating the efficiency of power usage in the circuit. A power factor closer to 1 means a more efficient system with less power being wasted. First, let's look at the formula itself. The formula for capacitive reactance is capacitive reactance equals 1 divided by 2 PIFC. This formula calculates the resistance to AC by a capacitor at a specific frequency. Now let's break down each variable in this formula. F, frequency, the rate at which the current alternates. The unit for frequency is hertz. C, capacitance, the ability of a capacitor to store an electric charge. The unit for capacitance is farads. Xc, capacitive reactance, the opposition that a capacitor offers to AC. The unit for capacitive reactance is ohms. This formula helps us understand how a capacitor resists the flow of AC at different frequencies, which is crucial in designing and analyzing AC circuits. Additionally, capacitors block DC from passing through because their reactance becomes infinitely large at zero frequency, DC. In DC circuits, capacitors are often used as filters to smooth out voltage variations or to store temporary energy during charging. First, let's look at the formula itself. The formula for inductive reactance is XL equals sine 2PFL. This formula calculates the opposition to current by an inductor at a specific frequency. Now, let's break down each variable in this formula. F frequency, the rate at which the current alternates. The unit for frequency is Hertz. L, inductance, the property of the inductor that causes it to oppose changes in current. The unit for inductance is Henrys. XL, inductive reactance, the opposition that an inductor offers to AC. The unit for inductive reactance is ohms. This formula helps us understand how an inductor resists the flow of AC at different frequencies, which is crucial in designing and analyzing AC circuits. Additionally, inductors can also be used in DC circuits for energy storage, storing energy in a magnetic field, useful in DC-DC converters. Chokes, blocking high-frequency AC signals while allowing DC to pass. EMI suppression, filtering out high-frequency noise from power and signal lines. First, let's look at the formulas themselves. All these formulas are used for power factor correction. Formula, Q equals VE sin theta. This formula calculates the reactive power, Q, using the voltage, V, the current 1, and the sine of the phase angle, theta. Formula, QC equals P times open parenthesis tangent phi 1 minus tangent phi 2 close parenthesis. This formula calculates the reactive power correction, QC, using the real power, P, and the difference between the tangents of the initial and final phase angles, phi 1 and phi 2. Formula, Q equals V squared divided by XC. This formula calculates the reactive power, Q, using the voltage, V, and the capacitive reactance, XC. Formula, XC equals 1 divided by 2 PFC. This formula calculates the capacitive reactance, XC, using the frequency F and the capacitance, C. Here's how to proceed with an example. Calculate QC if you have the values for VI and theta. Use Q equals VI sin theta to find the new Q. Subtract the old Q to get QC. Alternatively, use QC equals P times open parenthesis tangent phi 1 minus tangent phi 2 close parenthesis if you have the real power P and phase angles. Calculate XC. Use the formula Q equals V squared divided by XC with the known values of V and QC to find the required capacitive reactance. Calculate C. Use the formula XC equals 1 divided by 2 PIF with the known values of F and XC to find the capacitance required for the correction. By following these steps, you can effectively perform power factor correction to improve the efficiency of your electrical system. First, let's look at the formula itself. The formula for impedance in an AC circuit is Z squared equals R squared plus open parenthesis XL minus XC close parenthesis squared. This formula calculates the total impedance, combining resistance and reactance in an AC circuit. The formula for impedance in complex form is Z equals R plus or minus JX. This represents the impedance in terms of its real and imaginary components. The plus JX is used when inductive reactance is greater than capacitive reactance, and the minus JX is used when capacitive reactance is greater than inductive reactance. Now let's break down each variable in these formulas. Z, impedance, the total opposition to the flow of alternating current in the circuit. The unit for impedance is ohms. R, resistance, the opposition to the flow of current due to resistors in the circuit. The unit for resistance is ohms. XL, inductive reactance, the opposition to the change in current by an inductor. The unit for inductive reactance is ohms. XC, capacitive reactance, the opposition to the change in voltage by a capacitor. The unit for capacitive reactance is ohms. JX, reactance, the imaginary part of impedance representing either inductive or capacitive reactance. In conclusion, these formulas help in understanding the total impedance in an AC circuit. If the circuit includes an inductor, capacitor, and resistor in series, these formulas can be directly applied. For parallel LCR circuits, the calculations are more complicated, so we typically focus on series circuits for exam. Now let's briefly go through the Ohm's law wheel. The Ohm's law wheel is a visual tool for finding relationships between voltage V, current Y, resistance R, and power P. To use the Ohm's law wheel effectively, follow these steps. Identify the known quantities, determine which two electrical quantities you already know. For example, you might know the current Y and resistance R. Locate the desired formula. Find the segment of the wheel that contains the formula relating the known quantities to the unknown quantity you need to find. Apply the formula. Use the identified formula to calculate the unknown quantity. By following these steps, you can use the Ohm's law wheel to quickly and easily solve for the unknown quantity in an electrical circuit. Okay, now we have completed all the formulas in Group 1. Some formulas or steps may look quite complicated, but for the EWRB theory exam, it is actually easy. Each question in the exam is worth about 1 mark, so there should be simple questions using one formula directly. If you know each formula, then find that formula, insert the numbers from the question, and that's it. You don't even need to know the whole picture or all the steps for a complicated question. So please familiarize yourself with each formula first, that is the key.